When you're looking at rules for oxidation numbers, you know some of these rules already. And the ones that we're going to talk to you about today won't be all the new rules, but one of the rules, for example, is you already know would be number 6. Number 6 says the algebraic sum of the oxidation numbers of all atoms in neutral compound is equal to 0. So when we were balancing out charges, you guys already knew if they were ionic, like binary ionic or polyatomic compounds, they're all ionic because they're using polyatomic ions, that those all balance out to 0. All right? For example, if I have NaI, then I know that that overall charge of both of those put together is 0. So basically what you need to focus on that's new, that you're going to give some information for, is when we have nonmetals bonded to nonmetals. Okay? So we have practice determining charges based upon how they're matched up on ionic compounds. And those charges are known as oxidation numbers. Okay? You should know how to do that. If we looked at these to make sure that they balance out and it's written correctly, we'd look up iodine. And since it's bonded to a metal, makes it ionic, we say that iodine's oxidation number is what? Okay, come on. You should be able. What's iodine's oxidation number? -1. Any questions with that? Now, there's other numbers listed there. Okay? When you look at the sheet, maybe some of you are wondering why the 1, 5, and 7. Why do they have the 1, 5, and 7? Why don't we use those? We do now. Okay, we will now. So iodine could be also a +1, a +5, or a +7. Now, it will never be a +1, +5, or +7 when it's bonded to a metal ion or when a positive ion. It's always going to be a -1. Okay? Any questions with that? Na is going to be +1. In ionic compounds, we call those charges, and we can also call them oxidation numbers. Right? So here's an example where iodine would not be a -1. Now I need to explain it. You say, well, iodine's bonded to Na. No, iodine's not bonded to Na. IO3 is bonded to Na. And so if I would treat IO3 based upon what it looks like on the polyatomic ion sheet, IO3 equals what charge? -1. So IO3 is an ion, but iodine's not only bonded to sodium, it's a whole thing that's bonded to sodium, okay? So now, if we just looked at IO3 by itself, okay? And we know that when we add up the oxidation numbers, they need to add up to a -1. So if you look at Rule 7, it says the algebraic sum of oxidation numbers of all atoms in a polyatomic ion equals the charge of the ion. So if we add these two together, it must equal a -1. So we're going to have to determine what their charges are. Now there's some rules up above that we're going to go through real quick before we come back to this. All right? So some of the rules that we want to look at is, and I'm not going to list them. Number 1, according to what that is, but what we're going to do is say fluoride's always a -1, no exception. Give you an analogy for this, okay? I don't always do this, and I haven't always done it, but you know somebody that has a lot of character, no matter if somebody's watching them or they're by themselves, they do the right thing, okay? You know when you're dealing with that person, they're going to do the right thing, okay, all the time, okay, majority of the time. There's some, and that's why fluorine's always a -1. It always is going to be that way. Now there are some that have multiple oxidation numbers, and depending upon analogy, when you take a look at that, sometimes when they are with a group of people, they act a certain way, and when they're with another group of people, they act totally different. Do you know anybody like that?
Jacob. Yeah.
Okay. Okay. We don't want to throw out names.
Oh, sorry.
Okay. But okay, that would be a situation like in the wrestling room, and probably coaches in the basketball floor. When a coach is watching, they're hustling, they're working hard. Oh, he's watching, I better work hard. And then when they're not watching, I'm just going to take it easy. I'm not going to do the whole thing. Okay? I'm going to kind of take it easy. I've had a hard practice. I'm not going to work very hard. Okay? That's like hydrogen. Hydrogen, depending upon who it's placed with or what atom it's placed with, it can have multiple charges. So look in there. What does it say about hydrogen when it's placed with a metal? What charge would it be?
Hydrogen. +1.
When it's with a metal.
-1.
Okay? It is a -1 when with a metal. And the reason for that is because metals tend to want to give up electrons. And hydrogen will accept it. But H is a +1 when it's with what?
Compound.
Yeah, but with a non-metal. Okay? So that's a rule you need to keep in line. Most of the time, in our acids, what are hydrogens always linked with? Non-metals for the most part, or negative ions, so it's going to be +1. Okay? That H out in front. Okay? And then when we take a look at number 3, there's only a couple cases where oxygen will not be a -2. So for the most part, oxygen's a -2 unless it's a peroxide. Okay? And I'll give you a couple examples of that. Or one example. So oxygen is a -2. And then exceptions when listed as a peroxide. Okay, so on your polyatomic ion sheet you have in front of you, you have a polyatomic ion, 2 or more atoms hooked together to make a charge. Find peroxide. What is the formula for peroxide?
O2.
O2. And what's the charge of O2?
-2.
So each, that looks like CO2, it's supposed to be in parentheses, but each oxygen is what charge then. If our overall charge needs to be a -2, what's each oxygen's charge? -1. So if you look at oxygen, it can be a -2 or a -1, right, on that chart. The only when it's a peroxide. So if we have H2O2, now we just got done looking at hydrogen. We said hydrogen is going to be a +1 when it's hooked to a non-metal. It is, So the overall charge for hydrogen is a +2, and so oxygen O2 needs to be a -2 total charge, meaning each oxygen's a -1. Have you heard of hydrogen peroxide? Okay. Now, hydrogen peroxide is unstable. If you got it in your medicine cabinet, it probably won't stay as H2O2. Eventually, it will decompose into water. So basically, you have water after a while. Yep.
Isn't that much fun on cuts?
Yep. It is a disinfectant. Kill the bacteria in there, kill the bad stuff in there. Okay? So what I want to do is just do a little practice before you go, so that, and then give you 4 examples for you to do on your own. And we're not going to hit everything here. Tomorrow we'll do a lab associated with colors, and manganese can have 5 different colors. It's kind of cool. Manganese can form 5 different colors based upon its oxidation state. And if you look at manganese, it can be a 2, 3, 4, 6, or 7. And so we're going to manipulate the manganese, and we're going to cause it to gain electrons and lose electrons, and have its true color show up as that charge. Okay? You've heard of people that had multiple personalities. Have you ever heard of that before? There was a show a long time ago. It was called Sybil. You ever heard of that? The gal had like 9 different personalities that would come out. Totally different. I mean, they didn't know one from the other. They just come out. Okay, so that's kind of weird that you know that there's another. Kind of like Dr. Jekyll, Mr. Hyde. You've heard of that.
Yeah.
Right? Dr. Jekyll, Mr. Hyde. Okay, so manganese can have some different charges it can be. Right? So I'm going to give you, we'll go back to this example here and find out iodine's true charge in this example when it's placed with oxygen here in this way. So we know that IO3 needs to equal -1. We know oxygen is going to be a -2 because it's not a peroxide. And we have 3 of them, -6. So iodine has to be what oxidation state?
+1.
Nope. We have to have it equal a -1. What is it? +5, right?
Got
When
it.
we add our sum of our charges up, they have to equal the charge of the ion. Step 7 says it has to equal the charge. So in that case iodine's at +5. Okay, let's look at this one. NaIO2. So do we have IO2 on your list? We have IO4.
Yeah, we have 4.
Okay, let's make it IO4 since you have it on your list. We'll do it with that. There is an IO2, but since you don't have your list, I don't want to confuse any of you. So we'll make it IO4. So then what I like to do is to treat IO4 by itself and separate it from the metal. Because we know the metal is always it's going to be a +1 here. So I'm going to separate it out. Right, IO4 has to equal a -1. So now what's the oxidation state of iodine? So oxygen, 4 of them, -8. What is iodine? +7. Is there a choice there for +7?
Yeah.
Yeah. If you notice, I is with a non-metal. So iodine does not take on a -1 only when it's with a metal out in front. But if it's bonded to, most of the time we say oxygen we're going to deal with, that's what you're going to get. Okay? So always pull out the polyatomic ion to solve for that unknown in these compounds that have polyatomic ions in them. Okay? So what I'm going to have you do to practice this concept, this idea for tomorrow, is give you 4 examples where you're going to have to write the oxidation number of each element. Okay? Not the hardest one, but each one. Some of them you know for sure because you just look them up the periodic table. So, Na2SO3, COC2O4, CuClO4, 2.
Those parentheses.
Yep. And Ni2 SiO3 3. Now don't let the subscripts here mess you up. They are only there so that they balance out the charge of this first one. So you guys will have to determine, like you always have, because all these you'd have to name with a Roman numeral. So you still have to figure out the metals with the overall charge of the polyatomic ion. Okay? It's only when you have to figure like Si, Cl, C, and S that you just pull it out and treat it like an ion off the polyatomic ion sheet, like the 2 examples I showed you. Okay? All right. Go ahead and do those for tomorrow. We got a little lab that we'll do tomorrow.